Hey everyone, we are looking at another way to draw antiderivative graphs. So in the past we've drawn them by looking at slopes. Like we were like, okay, when x is 2, my slope needs to be 0. When x is 1, my slope needs to be about -1, and so on. It's not very fun. There's a more exact way of doing it. So this is how it works. So g of x is going to be the integral from 1 to x. So I'm actually going to start at x equals 1. So if g of x, so like g of 1 is going to be the integral from 1 to 1, which that sounds like kind of a weird thing to do, but whatever. So, from 1 to 1 for f of t dt, well, that's obviously a 0. So I can plot that. When x is 2, I'm going to work down and then I'll go backwards. So for x is 2, that means g of 2 is the integral from 1 to 2. For f of t dt. So if I look at 2, going from 1 to 2, I have about an area of about a -0.5. So I can plot that. Going to 3, I'm looking at the area from 1 to 3 of f of t dt, which actually I can look at that as -0.5 plus, because that was the integral from 1 to 2, plus the integral from 2 to 3 of f of t dt. So looking at 2 to 3 plus the -0.5, I end up with about, that's combined, call it 0.2, because that's about a 0.7. And then for 1 to 4 of f of t dt, I can look at that as, because I already know that 3 is at 0.2. And then from 3 to 4, that region is going to take me up to about 2.7 if I count up all my boxes. You can pause and count boxes if you want, or you can take my word for it. Okay, now we have to think a little bit harder and more carefully. Looking at 0, that's going 1 to 0, so that means we're going right to left, which means I have negative y values and I have negative dx values if you consider those Riemann sums. So really, even though this region right here is about 1.1 below the x-axis, but because I'm going from 1 back to 0, it ends up being a positive 1.1. Again, I can plot that. And then, which I kind of missed on my point. Yay for erasable pens. And then for -1, that's going from 1 back to -1 for f of t dt, which that would be another 1.1, so 2.2. And then for -2, I have another 0.5-ish that's going to increase, so that would be about a 2.7. So I can plot that, which takes me to, call it here. Looking at the shape I have here, so I know looking at this looks like a parabola. So this should look like kind of a cubic, which perhaps it does. I can try to draw it with a smooth curve. And notice here, like if this kept going, maybe I should have made this keep going, this would flatten out right here and start to decrease. So like just double checking things at 2 and -2, if that kept going, my slopes would be 0 on both of those spots. Positive slope to the right of 2 and negative slopes from -2 to 2 because I have negative values if you consider those slopes again from way back when we were looking just at the slopes. But looking at antiderivative graphs as this accumulation of area as you go from one point to the next, you go, okay, right now I'm at -0.5. How much area am I going to increase? I will go up that much, and so on. It's way more exact than having to just kind of futz around looking at those slopes. Okay, Another part of the puzzle here, and this looks a bit like what we just did on our previous video. So if we want to find h prime of 1, if h of x is the integral from 1 to x cubed of f of t dt, so if I want h prime of -1, I should start with h prime of x, which will be f of, this is using that second form of the fundamental theorem, so plug the x cubed in for t, and then plug the derivative of it for dt, so 3x squared. So now h prime of -1 is going to be f of -1 cubed times 3 times -1 squared. F of -1 cubed is -1. F of -1, looking at this graph, let's pretend it's exactly at -1 for the sake of convenience. I know it's not quite there. Times 3, and we get a -3. So there is our derivative of an integral again, but this time when we're just working on a graph from a graph, but it's no big deal. So we have another way to draw antiderivative graphs, and we also have just another example of that second form of the fundamental theorem.